All right, 9.4, we started last time. We were looking at permutations and combinations. We had done one example, and our example that we had done, we had done the fundamental principle of counting actually first, where we talked about different ways that things can happen as a counting technique. The first one in terms of the description of our section was permutation of like objects, and we talked about different kinds of candy and the different flavors being alike. There's some other examples of that. So one of your book talks about is some different flags where you have a bunch of red flags or a bunch of green flags, those kinds of things. We actually did another example as well where we were looking at men versus women going to a trip, right? And remember we had the situation where the individual people didn't matter, but it mattered whether they're a boy or a girl that went, that kind of thing. So that can kind of come into play. We were just talking a minute ago about makes of cars. So if you were talking about a car race and you were wondering to know which car was going to win, but all you cared about was who made the car, like is it Ford, is it Chevy, that kind of thing, that would actually be another example of like objects. So it isn't always that the objects are identical. Sometimes it's just that the characteristic you care about is identical, all right? So some objects, however, though, are not alike at all. So the next one is permutation of unlike objects. So in this scenario, it really does matter which car it is, not just which make of car. It really does matter which person from that university won the medal. It just doesn't matter that the school won that medal, right? And so if this is the case, we have a formula that looks like this. So this is n elements chosen r at a time. So it says NPR, they both are subscripts. The subscript before the P is subscript after the P. The number before the P is the number of total objects you have. So this is our total, we'll call them elements since we've already called them elements here on the paper. And then R is the number we choose. Right, so in a given class, you have 24 children and you have to choose 2 people to be the students of the month. Yeah? You have to choose a total across the year of 10 students to be the students of the month. Right? The individual people are different this time. They actually really are different selections. What you see in the formula over here is you see that n factorial, the total number, is on top. And the denominator, you see the subtraction of that. Or you can also think of this as this n minus r is the number that are unchosen. How many did not get picked? How many did not win? Or whatever your scenario is. And it's a factorial. Just like with the factorials over here, it'll always reduce to a whole number, which means your denominator will always cancel with the numerator. If at some point you decide you don't want to worry about the canceling and you just want to multiply across the top, multiply across the bottom, you can. But sometimes the numbers are too big and you can't do that from the get-go. So we're going to take an example. We have contestants who are in a raffle, and first place wins $100. Second place wins $50. And third place wins $25. Now, I haven't made mention of it, although it was on the other slide in bright red and like bold and big print and everything, and it says order matters. There's a comparison we're going to make in a moment where order doesn't matter. The order of this selection, though, you can see why it matters. If you win first place, you win something different than you win third place, right? Now, everybody who doesn't get chosen, doesn't matter what order in which they didn't get chosen, they just didn't get chosen. But for the 3 winners, the order matters. It's not just I selected all 3 of them and they got the same prize, or they all got to go on that vacation, or they all got student of the month, right? It looks a little bit different if the order matters, and this is an example where the order matters. So we have 30 contestants, but not all of them win, right? Okay, so there are 30 people that we're selecting from. How many win? 3. And the order does matter because the selection of the order of which we pull them out for the raffle determines what their prize is. So the numerator is the entire grouping of the 30, and the denominator is the number of people who don't win. So how many people don't win anything? 27. If you need or want to write out 30 minus 3 and put the factorial, feel free to do so. That's fine. And like we did last time, we're going to write this number out until we get to a number that can easily cancel with 27 factorial. In particular, we're looking for 27 factorial. So this 27 factorial cancels with this 27 factorial. And we multiply 30 times 29 times 28. And what do we get? 24,360 different ways to select 3 winners. Now, in some of those ways, it's the same 3 people, right? They're just a different ordering of prizes. But in some of those ways, of course, none of those people are winning as well. Those are all of the different ways that the winners could be selected. Now, in a combination, the order doesn't matter. So one of the words that you've heard, or the objects that you've seen before, is called a combination lock. A combination lock is not a combination. It's a terrible misnomer, actually, terrible. It's actually a permutation lock, by the way. If you were to call it by its real, like what you're doing. The order matters on the combination lock, right? You can't just do it in whatever willy-nilly order you like. I mean, it's not going to work. So don't think about these things with that context. But it is a situation for a combination where the order doesn't matter. So if you notice the formula is quite similar to the formula we had before, right? I still have the n factorial on top. I still have the n minus r factorial on bottom. But now I have the r factorial on bottom as well. So it's the number of ways that we don't have winners, right? The number unchosen with a factorial. And we also have the number chosen with a factorial. Because the order doesn't matter, we eliminate some of these things that can happen. So in the scenario over here, every combination would have everybody winning the same number of value of money. Maybe they all win the same value. That's the problem we're going to do here in a second. Which means that it doesn't matter if I select Lauren first, Addie second, Kessie third, or if I select Kessie first and Lauren second and Addie third, right? None of that matters. It becomes irrelevant, that ordering. So we eliminate some of those double countings by dividing by r factorial, okay? So the problem we're going to work at is just that. We still have our 30 contestants. All the people are winning, but they're winning the same amount of money, the 3 people. And so in this scenario, the order doesn't matter because they're all winning the same thing. So we still have 30 people. We're still selecting 3, but it's a combination. So 30 factorial is still on top. This time, though, what's on bottom? 27 factorial and 3 factorial. Now we're still going to write the 30 out till we get to the 27. 30, 29, 28, and 20. I'm sorry, that was a 8. 28 and 27 factorial. And there's the 27 factorial still. And then I'm going to write the 3 out, 3, 2, 1. We saw this happen on the starburst example. So the 27 factorials cancel. This is a place where if you really wanted to just multiply the numerator, multiply the denominator, and divide them, it would totally work just fine. You could also remember that 3 times 2 is 6, and 6 very nicely goes into 30 5 times. So you could do that if you wish. The one thing to be careful of is that when you're going back to figure out what I'm multiplying together, that you make sure you catch all the things you're supposed to be multiplying. So be careful with your handwriting, write neatly, write cleanly, those kinds of things. So what do I get if I multiply 5, 29, and 28? 4,060. And it makes sense there's fewer ways because the order of selecting winners is irrelevant now, as well as the order of not selecting others. So there are fewer ways to do this then. All right, here's another example. In fact, I think we're just doing examples for the rest of them. Yeah, the rest of them are examples. So that's all of the topics that we're looking at. What we have to decide now when we're doing problems is which of the different ways are we going to use? We have 4. 2 of them we did last time. One of them was fundamental theorem of counting fundamental principle of counting. The second one was permutation of like objects. Okay? And then today we've done two. We've done permutation of unlike objects where the order matters. And we've done a combination where the order doesn't matter. And occasionally there's more than one way we can do a particular problem. Occasionally. So we're going to take a look at number 6 and see if we can figure out what it is we would need to do to answer this question. If all the phone numbers in a large business start out 405767, and it has 4 more digits at the end, right? So they issue out cell phones. Everybody has the same first 6 numbers, right? 4 last 4 are different. How many different phone numbers are possible? A lot is a good answer. Not a precise answer, but it's a good one. Yeah? How can we figure it out?
Use the permutation of unlike objects.
So the catch with permutations is that once you use an object, you don't reuse it. So think about like once we once we selected a winner in that scenario, they don't win a second game, right? They don't win a second time because their raffle ticket's already been pulled. In this scenario, we can reuse the number. It would be creating a different number. I mean, it would not hinder us from creating a different number to reuse a number.
So combination.
Combinations have the same feature, actually. We still don't reuse them when we are selecting our winners. Something from last time. It's fundamental principle of counting. In fact, a fundamental principle of counting is the only one that reuses objects. So if you want to jot yourself down a note that if you're reusing your objects, it has to be the fundamental principle of counting. That's a good recall item. There are 4 different numbers that we're selecting. How many different number options, single-digit options, do we have in each location? 10. We have the digits from 0 through 9, so that makes 10 digits. So I have 10 choices for each of my 4 last numbers. And the fundamental principle of counting says that I multiply those 10s together. So what is 10 multiplied by itself 4 times, besides being 10 to the 4th? Yeah, it's 10,000. There are 10,000 numbers. You could have a fairly big company, right? And still I'll share those first same 6 digits. Okay, so there's a learning curve in picking solutions, so please keep trying. Just because you got it wrong last time doesn't mean you can get it wrong next time, okay? So let's try another one. A worship team practices 8 songs on a Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? What do you think? Same one as you can use a combinate. That's not the word I wanted. A fundamental principle of counting. That is one option. So there are 5 songs that they're going to play in church on Sunday, right? How many options does the worship minister have for song number 1? 8. Song 2? It's actually 7. He wouldn't repeat the song, or he would just be singing the same song. That's kind of the way songs go, yeah. And then after that, we'd have 6, 5, and 4. So go ahead and multiply those together. There are 6,720 different orderings of music that this worship minister could choose. There is another way to do this problem. This way is perfectly fine, by the way. I'm not discouraging you from using it. But there is another way to think about this problem. We had to do this one with the fundamental principle of counting because we had to be able to reuse the numbers, right? Over here, notice we didn't have to reuse our numbers because of the way songs are working for us, right? So we do have another option available to us on this one. Any idea what it might be?
Permutation.
Which kind of permutation? Of unlike objects. Yeah, it is a permutation of unlike objects. permutation as opposed to combination because the order matters. That's what I'm finding. I'm trying to find the number of ways these can be ordered. Like that's in the description, right? And it's unlike objects because the songs are not the same song, right? It's not 8 of the same song. Like that doesn't even make any sense, right? The context wouldn't work for that. So if we thought about it from that perspective, it would look like this. You'd have 8 and you would do a permutation choosing 5 of them. So you'd have 8 factorial on top. And how many are you not choosing? 3. And then when you write this out, you write 8 times 7 times 6 times 5 times 4 times 3 factorial. The 3 factorial is going to cancel, and what does it look like? Exactly the same thing we had in the problem above, or the other version of it above, right? Yeah. So 2 different approaches, but they both work on this one. Occasionally that happens. All right, our last example is a long example because it's a really, well, not the last example. Our next example, I have one more after that, is a long example. It's got 3 parts to it because it's very conducive to creating multiple parts because we're talking about a card game. So we have a standard deck of cards, standard deck of 52 cards. We've talked about cards before. We talked about them back in 9-1. So I won't belabor you with repeating everything, but I might mention a few things here and there. We do have 52 cards. And on part A, we're trying to find how many different 5-card hands can be dealt. Okay. So which of these types of problems, we have 4 types, is this? Okay. Okay, I agree that it's unlike objects, but I don't know that I agree that it's a permutation. So if it's unlike objects, we must be looking at then a combination, right, Kate? Why would this be a combination and not a permutation?
Because the order isn't matter.
Right. What's the first thing you do when somebody deals you a hand of cards in playing any game? You reorder it, right? Whether it's Old Maid, right? Or Slapjack, or, well, maybe not Slapjack because they're supposed to be hidden if you're doing Slapjack. But the first thing that happens when you have a hand of cards like this that you're working with Skip-Bo, is you put them in some kind of order, whatever the game, necessitates that you do. Uno. We do lots of card games in my family. Yeah, so that's why the order doesn't matter. The order doesn't make any difference on these. But they are unlike objects, right? All the cards are different, specifically in this game, right? This isn't Uno or Slapjack or not Slapjack. I don't know why I keep saying that one. This isn't Uno or something where the cards double up, they do match each other. It's really 52 different cards, completely different. So we have 52 cards. And it is a combination since order doesn't matter, and we are choosing 5 of them. What goes on top? 52 factorial. What goes on bottom? 5 factorial is part of it. 52 minus 5 is also part of it. So what's 52 minus 5? 47. Okay, so we both put the number of cards I am choosing with the factorial and the number of cards that I'm not choosing with the factorial on the bottom. And then we write this is an example one. If you put this in your calculator, 52 times, not to mention that it would be really long in doing so. You might find the factorial button in your calculator. That might help you out. But even if you do, it will give you a scientific notation answer. It won't give you the answer because it's too big. So it will not work in your calculator the way this is written. You have to do simplification. So we're going to do 52 times 51 times 49 times 48 times 47 factorial over 47 factorial. And then we have 5, 4, 3, 2, and 1. All right, so our 47 factorials cancel. Let's see if we can reduce. You could multiply the top, multiply the bottom, but let's see if we can reduce these. Do you see any number that will cancel with your 5? Oh, I skipped one. Did y'all notice I skipped one? Thank you. Nobody said anything, though. Glad you noticed. Noticing is part of the problem. All right. Okay. I noticed right now, though, because I went looking for what 5 was going to divide into, and it didn't work, right? Yeah. The 50 is what I need. The 5 will go into the 50 10 times. What else will divide out? The 4 and the 3. 4 times 3 is 12. What will 12 reduce with? 48. You can do them piece by piece or you can do them in pairs. We need something to reduce with the 2. We got lots of choices. Which one do you want to reduce? The 2 with the what? The 52. Okay. What is 2 divided by 52? 20. Sorry. What was it? 26. I was about to write it right. Yeah. Okay. All right. So we go back and we grab all the ones I need. Here I have 26, 51, 10, 49, and 4. And if we multiply those, what do we get? It's a big number.
$2,598,960.
You read that very well. Good
It
job.
took my brain a second.
It's okay. Lots of digits. There are 2.5 million different hands of cards when you play cards. That is crazy. Yeah. Which starts to explain why there's so many games and so many things you can do with just 52 cards, because it's a lot of hands of cards. Okay. What if we want to know, though, specifically how many 5-card hands are only diamonds? Okay, so when you play certain games, like poker, right? You're trying to create, or Texas Hold'em, that's another one too. You're trying to create decks or cards of hands that are the best case scenarios of things that are rare or uncommon. If you get 5 cards that are all the same suit, that's called a flush. Would be a diamond flush. Okay. So I want all my cards. I still want to choose 5 cards, but I want them to be all diamonds. Do you remember from 9.1 or just from your knowledge of cards how many diamonds there are? 13. There are 13. So there's 13 of every suit. So still order doesn't matter. Order's not going to matter for the whole problem. I still have 13. So this one I have 13. The order still doesn't matter, so I still have a combination. And I'm still selecting 5 cards. So at this point, what goes on top? 13 factorial. What's going to go bottom? Yes. All right, so the 8 is how many I didn't choose. 13 minus 5, and you can feel free to write that down if it's helpful. And the 5 is how many I did choose. So I'm going to write my 13 out until I get to 8. 13, 12, 11, 10, 9, and 8 factorial. Over 8 factorial, and then 5, 4, 3, 2, and 1. So 8 factorial is canceled. That's my first cancellation. The denominator pieces actually pair up really nicely on this one. Can you tell me a pair that you can see really nice? 5 and 2 actually both make 10. So if we do the 5 and 2, I can cancel out the 10 completely. What can I do then with my 4 and 3?
12.
Yeah, the 4 and the 3 make the 12. Yep. So looking back at this, I only have 3 numbers. I have 13, 11, and 9. How many will that give me?
1,287.
1,287. That's a lot, but it's nowhere near 2.5 million. In fact, that's our next example. We're going to try and figure out how likely that actually is. What is the probability that I get this to happen? So what's the probability of getting all diamonds? Well, I need the number of ways I get the number of all diamond hands. And divided by the number of all hands. And in fact, those are the 2 things I just found in parts A and B above. How many all diamond hands are there?
1,287.
And how many all kinds of 5-card hands are there?
2,598,000. Like that number.
Mm-hmm. 98,000, you're right, and then 960, yeah. So you definitely need your calculator to do this for you. We're going to turn it into a decimal. We are going to use 4 decimal places because you're going to need them. It's a very small number. So if you multiplied it by 100, you would get 0.05. I'm just going to give you a reference point. This is 0.05%. 0.05% chance of this happening is very, very small, right? Yeah, it's very small. So 0.0005 is our probability. All right, we have one more example. I think we can still do it in our next 6 or 7 minutes here, and then we'll make group work and homework all together as homework to be done on Monday. We won't be having class on Friday. Okay, no class Friday. All right. A committee consists of 3 people, and it is selected at random from 7 seniors, 5 juniors, and 3 sophomores. What is the probability the committee consists of all seniors? So this is actually asking the same thing as question C here. It's the probability of comparing some things. Okay, C here compared 2 things, the number of diamond hands to the number of all hands. This one's comparing the number of all the committees to the number of committees that only contain seniors. All right, so what we're looking for is the probability of an all senior committee. But the only way we can do that is by finding the number of all senior committees, right? How many of those are there even possible? And the number of all committees. I should say all senior committees. I'll abbreviate COM. And this is the number of all committees. So those are the 2 things we're going to find first. We're going to find the number of committees that have all seniors. Well, how many seniors are there? 7. How many am I choosing? 3. Do I have a permutation or a combination? Okay, I hear both. So Cassie's the one who has the right idea, so I want you to explain, though, why you think it's a combination. Yeah, in a committee, it doesn't matter what order you're put on the committee in. You're on the committee or you're not. If you were putting people into roles in an organization like president, vice president, secretary, treasurer, then order would matter. But in a committee, it doesn't. So we do have a combination. So this is 7 factorial on top. We don't choose 4 of them. We do choose 3 of them. So 4 and 3 on bottom. 7, 6, 5, 4 factorial over my 4 factorial, and then 3, 2, and 1. The 4s cancel. What else can cancel? The 3 and the 2 at the 6. Imagine you can do that one in your head. 7 and 5 multiplied give me what? 35. There are 35 committees here that would be all seniors. 35 different committees would be all seniors. Or different arrangements of people to create committees, if you wish. We also need the number of all committees. Whoops. Okay, well, how many total people are there? How many? 15. And how many am I choosing for my committee? 3. And still committee, doesn't matter the order. So we are going to do 15 factorial. How many do not get chosen? 12. How many do? 3. So I have 15, 14, 13, and then I have 12 factorial over 12 factorial. And 3, 2, 1. 12 factorials cancel. What will the 3 cancel with? The 15, which will leave me a 5. And the 2 will cancel with the 14 to leave me a 7. So I have 5 and 7, which is actually 35. And then I have the 13. What does that give me? 455 committees. Now I can return to what we did at the top, and we can actually fill those in, what I was trying to find anyway, which was the senior committees, which is 35, divided by all the committees, which is 455. And we'll represent it in a decimal form. It makes sense contextually to talk about that. So what is the decimal value I get with 4 decimal places? Most of these are going to be asking for 4 decimal places, so.
10769.
Good. And if we multiply by 100, we'd see that this is about 7.5%. It's not very likely that the committee is only going to be seniors, right? Part B to this question has already half of it done. This wants to know the probability that it has no seniors. Well, in order to have the probability of no seniors, it would mean the same thing as having the probability of having only freshmen and sophomores, right? That's what no seniors means. So on top, I need the number of ways of having only freshmen and sophomore. And on bottom, I need the number of ways of having all committees, but I've already found that. That was 455. So the only calculation I have to make for this one, because I've done work on already on the problem, is the number of ways of having freshmen and sophomores. How many freshmen and sophomores are there?
Well, there's only 3 sophomores that they have.
Okay. I'm sorry, I didn't mean freshmen. I meant juniors. I got the wrong letter. Juniors is what I meant. I'm so sorry, guys. That's what happens when you try to hurry. Juniors and sophomores. Okay.
Okay, so then 8.
Yes, no seniors. So there are 8. It should be 8. Yeah, thanks. I have a committee, so I have a combination. Still choosing 3 of them. 8 on top. How many do I not choose? 5. And I choose 3. So I'll write my 8, 7, 6, and 5 factorial to match. My 3, 2, 1. 5 factorials cancel, and what else do you notice cancels? 3 and 2 was the 6. So I have 8 times 7. What is 8 times 7? 56. So this is slightly more likely. It's still not real likely. You'll see in a minute. But it's slightly more likely because I have 56 on top instead of 35. What is 56 divided by 455? 4 decimals. What was that? 1, 2, 3, 1. So it's about a 12% chance, right? About 12% chance of it happening. That's my probability here. Okay, so while we didn't get to the group work, we don't have class on Friday. So we do have 5 days between now and when this is due. This is a hard section, and I would really encourage you to not wait till Sunday night to do this. If you do, you're going to feel yourself very frustrated, and you might be cursing my name. I mean, I hope you're not cursing my name, but you might be really upset with me. So that's why I'm warning you right now. The Success Center has lots of hours if you don't wait until Sunday night, okay? All right, we'll be doing a review for the test on Wednesday. The review is Monday, the test is Wednesday. And next Friday, there's no class, because next Friday is Easter. Well, it's Good Friday, okay? All right.